Okay, here's a star that's known as Corot 7. Now this particular star was discovered by a space telescope called Corot. The C in Corot stands for convection, and convection is the process of heating up a liquid or a fluid of some kind, and it goes around and around and around. So that's what convection is. Then the R stands for rotation, and the T stands for planetary transit. Okay, so C-O-R-O-T. And this was a French telescope that was launched and went into outer space and took observations from outer space. So now this particular star is about 520 light years from Earth. Okay, and it happens to have 3 planets that have been discovered orbiting it. And we're going to discuss the planet that's called Corot 7b. Now, Corot 7b is interesting because it is potentially known as a super-Earth. And a super-Earth means that it is more massive than the Earth. They think that this is somewhere between 2.3 to 8.5 times the mass of the Earth. And the symbol that astronomers use for the mass of the Earth is the mass symbol with the subscript of a circle with a cross in it. Okay, so as it turns out, the orbital radius, or in other words, the semi-major axis of this star, is 0.0172 astronomical units, and the period of the orbit is 0.854 days. So we're going to use these 2 bits of information to calculate the mass of this star Corot 7. So we'll move over here. Now the first thing that we want to do is we want to convert the radius, which is given here in astronomical units, we want to convert that into meters. And the way we do that is we multiply the amount or number of astronomical units by the conversion 1.496 times 10 to the 11th power. So we're going to do that here. Oops. There's my calculator. And we're going to do that by 0.0172 multiplied by 1.496 times 10 to the 11th. You'll notice that when I did times 10 to the 11th, I pushed the EXP key. So here I'm going to hit the equal sign, okay, and that gives us this number, which is, that's a big number. Okay, that's in billions. That's 2,573,120,000 meters. But we want to change that into scientific notation. On this calculator, the way we can do that is by hitting this FSE button. If I hit it twice, it converts this into 2.573 times 10 to the 9th meters. Okay, and we'll come back and use that particular quantity in a bit. So I'm going to hit the FSE key again and put it back into decimal notation. The next thing that we want to do is we want to take 0.0854 days and convert that into seconds. So T is 0.854 days. Make sure I got that right. That's 0.854. And we're going to multiply that by 86,400 because there are 86,400 seconds in one day. So again, we'll do the calculation here, 0.854 multiplied by 86400. Okay, and we get this number, 73,785.6 seconds. And I suppose we can keep it that way. 0.6 seconds. Okay, so how are we going to calculate the mass of this star? Well, the equation that we're going to use is the mass m is equal to 4 pi squared over capital G, where capital G is the Newton's universal gravitational constant. And then we'll multiply that by r cubed divided by t squared. Now this is a modified form of Kepler's third law. Kepler's third law. Okay, so first of all, let's calculate what 4 pi squared over g is, because this we can use over and over again in several of these stellar mass calculations. Okay, everybody knows that pi is approximately 3.14, and g turns out to be 6.67 times 10 to the negative 11 power in MKS metric units. MKS stands for meters, kilograms, seconds. So that's the type of metric units that we're measuring these in. So now, when I do the calculation, I'm not going to use this rounded off value for the number pi. I'm going to use the number that the calculator gives me, and I can do that by going shift, and then when I hit the 1 key, it tells me what pi is. So then I'm going to square that, multiply that by 4, and then divide that by 6.67 exp negative 11. And that gives me 5.9188, I'm going to round it off at that point, times 10 to the 11th power. Okay, so we're going to need this number, and this number for our stellar mass calculation. So let's move to a new piece of paper. Okay, and so our equation again was m equals 4 pi squared over g multiplied by r cubed over t squared. And we can say that that's equal to 5.9188 times 10 to the 11th power multiplied by r cubed, and r, if you recall, was back here on this other piece of paper. It was 2.573 times 10 to the 9th power. So we'll write 2.573 times 10 to the 9th power, but we're going to end up cubing that. And then the value for the period was right here, 73,785.6. So we'll put that here, 73,785.6, and we're going to square that. Okay, so the question is, how are we going to do that? Well, here on this calculator, I'm going to start with the radius and cube that first. So we'll enter that, 2.573 exp9. Okay, and on this calculator, there are two different ways that I can find this number cubed. I'm going to use the y to the x key, and then hit the number 3, and hit equals. Okay, so that was 2.573 times 10 to the 9th, and then we cubed that number. Now the next thing I want to do is divide by the period squared, and in order to do that, I'm going to divide, but I'm going to use the parentheses. So in the parentheses, I'm going to enter 73,785.6, and then I'm going to square that, close the parentheses, and hit equals. Okay, so these two numbers, the numerator cubed divided by the denominator squared, ends up giving us this value, 3.128787964 times 10 to the 18th. Okay, but now we've got to multiply that by this number, which was the result of doing 4 pi squared over the universal gravitational constant. So we'll multiply this now, excuse me, by 5.9188 exp11, and there's our solar mass. So the solar mass of Corot 7, I'm going to round this off to the nearest hundredth. It'll be 1.85, and that was an arbitrary decision. But I'm going to just round it off to the second decimal place after the decimal point, which is the nearest hundredth. So and then we'll multiply that by 10 to the 30th power, and the unit for this result is kilograms. Okay, and then let's compare that to the solar mass. The symbol for our sun that astronomers use is the circle with the dot inside of it, and the solar mass, the mass of our sun, is 1.989 times 10 to the 30th kilograms, and I'll abbreviate kilograms as kg. And what that tells us is that this was for Corot 7. The mass of Corot 7 is pretty close to the mass of our sun, right? It's not quite as large, so it's a little bit smaller, but it's in the same class of stars, right? These are called G-class stars, right? So it's not quite as large, and it's not quite as bright, but it's close. So that means that it's possible that a star, or rather a planet, is within the Corot 7 solar system could possibly have life on it, or might be able to support life if we were to go there and terraform it or something like that. Okay, so this was our result, and you saw the process by which we can use Kepler's third law to calculate a stellar mass based on the orbital radius and orbital period of a planet that orbits that particular star.